homework series 3 in advance of the test quiz, homework quiz on October 26th. So this is actually homework 1. I'm a little behind on making these videos and I apologize, but I'm going to try to keep up. So going all the way back to the first thing, we're talking about vertical and horizontal asymptotes or slant asymptotes. So unless you watch the videos that each of the group members have made, you might be a little behind on this, but we have enough to proceed forward because we could have a good sense if we're talking about vertical asymptotes, we're talking about zeros of the denominator, things that you can't divide by. And if you're talking about horizontal asymptotes, you got to do some kind of division. All right, so let's go ahead and deal with our vertical asymptotes first. And so the idea behind the vertical asymptotes is that the one thing you can't have is like something divided by 0, because division by 0 is an undefined thing, which means we can't do it mathematically speaking. And so the real idea is if we're going to find a vertical asymptote, we're going to find domain violations. We have to look at our denominator and ask ourselves what values of x will make this 0. Now in this current form it's a little bit difficult to ascertain. What we can do, noticing it's a fully built quadratic, we can go ahead and try to factor this. Now you could use quadratic formula completing the square, but this one does factor quite easily. We have x and x to make our x squared. 2 and 3 make 6, and plus 2 plus 3 makes a plus 5 in the middle. And so if we look at our f of x value, our f of x function, excuse me, as x squared divided by x plus 2, and then x plus 3, we can see that the values of our zeros for this will be x equals -2, and this will be x equals -3, meaning those are the two values I cannot use for x in the denominator because those would make our value equal to 0, division by 0, which is undefined. And so our vertical asymptotes, we actually have two of them. We'll be at x equals -2 and x equals -3. So to give you kind of a graphical sense of what's going on, if I go to -2, there will be an asymptote, and then if I go up to 3 again, there'll be another asymptote. I'm not holding you responsible for knowing what the graph looks like quite yet, but please know those are where the vertical asymptotes are anyway, and those are the only two values I can't use for my domain. Now I do want you to also find horizontal or slant asymptotes, and again if you watch the student videos related to this, you get a better sense of the shortcuts. At this point you may not know them, but what we might know is that we really have to perform polynomial division. And so if we take x squared and we divide it by x squared plus 5x plus 6. In other words, we perform a reduction. We can reduce x squared to just 1 because that's going to be x squared minus 5x, plus 5x plus 6, and then minus 5x minus 6 for our remainder. Point being, we're going to reduce it to 1. So it turns out that's actually going to be our horizontal asymptote. So our horizontal asymptote is going to be at x equals 1. Now there is a way we can determine that by looking at our function, but that's something for a later time. Let's do it again. So we need vertical asymptotes, we need slant asymptotes. So the vertical asymptotes I think have been well established. We need to look at the bottom and ask ourselves what's the x value that would make that 0. In other words, what's going to make this something over 0, an undefined value. And in this case, it's really straightforward because it's already basically factored for us. So our one vertical asymptote, it will be at x equals 4. To find a horizontal asymptote, we're going to have to perform division, unless you have ascertained that shortcut. But we can divide this. That's not a big deal. X minus 4 is a divisor of x squared minus 6x plus 1. And so that'll go into it x times. X times x is x squared. X times -4 is -4x. We end up with a remainder of 2x plus 1. Okay, and so we'll do it one more time. So x goes into -2x, -2 times. So that'll be -2x, and this will be plus 8. And so our final remainder will be -7, which turns out not to matter too much. This ends up being our slant asymptote. So the horizontal asymptote, which is actually a slant in this case, is going to be y equals x minus 2. Okay? There's more explanation to come to this later. The procedures, what this particular homework is going to focus on. And so as we proceed in the homeworks and you have a chance to look at those notes, this will make more sense conceptually as well. All right, let's move on to some stuff for preparing for the future. We have this function f of x equals 3x squared plus 2. The first question is really just for you. It's not one that I'm going to talk through too much. But I still want you to do this one, of course. I want you just to think, If you plug in 3 and you plug in -3 for x and run those through the function, will you have the same result or will you have different results? And so you might look at features of the function that might help you determine this. The one feature that you might want to key on is the fact that you only have one x and it happens to be squared. And so you can certainly ask yourself, what will happen to an x value when I square it? But we can also just test it. So if I test f of 3, instead of having 3x squared, I'll have 3 times 3 squared plus 2. 3 squared is 9. 9 times 3 is 27, and so I'll end up with 29. We can also test that against -3. So 3 times -3 squared up plus 2. Well, -3 squared is still going to be 9, because even if it's a negative, squaring multiplies by itself, so a negative times a negative is a positive. Multiply that result by 3, you get 27, add 2 and you get 29. And so in step A, if you guess that they're going to be the same value, good for you. If not, try to think really hard about why they are the same value. And again, I point back at the fact that we have this 1x value and it's being squared. And so you can think about the effect squaring has on a number, whether it be positive or negative. All right. So we want to talk about the maximum minimum points of the graph below and talk about the end behavior as well. So let's kind of make sure we're understanding where these things are coming from. And so these right here, these pieces I'm drawing in, these are going to describe the end behavior. Okay, so these, as the graph increases towards negative or positive infinity, what's going on? Please understand also when we talk about end behavior, we're talking about the y value, like what's happening with the y value as those numbers get very big. When we're talking about local maxima or minima, maximum or minimum, we're talking about the biggest or smallest points in the graph. That's not really talking about end behavior. So we're talking kind of in the small picture, the laser focus area. In that area, is there a high or low point? Well, it turns out there's a couple. So right here we have a high point, right here we have a low point. And again, when we're talking about maximum and minimum points, we're still talking about the y value. And so it looks like, So it looks like in this type of work, we're always concerned with the value of the graph, not necessarily the x value that gets it there. Although the x value is the thing that's going to be part of this analysis as well. So let's talk about end behavior first. Okay. So we have a couple things that's going on. Now remember, we want to use proper notation, so I'm going to talk about the limit as x goes to one place or the other. So we can talk about the limit as x goes to infinity. We can also talk about the limit as x goes to negative infinity. Okay. Negative infinity. So positive infinity is going to be this piece right here. Like what's happening is that goes there. Now we don't really see a leveling off. We see it's decreasing, but we can't really ascertain more than that. And so it'd be fair to say the limit as x goes to infinity of the function is going to be negative infinity. Like we can't really tell if it's leveling off or not. Let me erase some of this stuff. It kind of looks like it might, but we don't really know for sure. So I think our best guess is that's going to kind of continue in this downward fashion to infinity. If we go this way, okay, we can say the function, limit of the function as x goes to negative infinity is going to be positive infinity because we see it's going up. It doesn't look like it's bounded in any way, like it's going to be limited. Therefore, the limit is going to be infinity. Okay. Let's talk in terms of maximum or minimum behavior. It looks like we have a maximum about right here, and so we probably just want to take our best guess on like what those values are. So it looks like about right here on the x, about right here on the y, and so it would be fair to say this value is 1.25, because if that's a half, that's a quarter, and then looks like 7. So it looks like we have a max at 1.25, comma 7, and our minimum is right here-ish. And so we can say we have a minimum, looks like it's going to be about negative 0.25 and 0.25. Negative 0.25 and 0.25. And those are just guesses, of course. The important thing to note is how to actually perceive the idea of maximum and minimum. All right, let's talk about some old stuff. So it seems we got to keep in mind for our review. Sketch and find the domain and range of this function. Well, it's important to note that if we're going to graph that function, we should know where it starts, with just x squared. We should also note that if we're talking about x squared, the domain of x squared is going to be negative infinity to infinity, and the range of x squared is going to be 0 to infinity. These are important things to keep in mind. Have them in notes or have them kind of at the ready in your head, kind of by memorization. because it's going to make your job a whole lot easier. All right. So if we want to graph the parent, which is a good thing to do, we're looking at a parabola that has a vertex at 0, 0. So now if we take this new function, this f of x equals 3 times x minus 2 squared plus 1, and we think about where the pieces are coming from, remember that's going to affect your x, so that's going to move it left and right. That's going to affect your y value, so it's going to move it up and down. And that's going to be a multiplication factor, which is going to stretch or shrink it vertically. And so we can do some analysis here. We have x minus 2, so that's going to move it to the right 2 units. We have a plus 1 at the end. That's going to move it up 1 unit. And then we're going to have a times 3 on our values because we have this multiplier of 3. And so we'll see, move it to the right 2, and then up 1. And then it's going to be skinnier. Now, this is just a sketch. We don't have to concern ourselves too much with the exact points. We do want to track our vertex and make sure we know that's going to be at 2, 1. And as long as we perceive it to be skinnier, that should be okay for a sketch. Because sketches, hand graphs, they're just for problem solving. Here we need to find the zeros either by completing the square quadratic formula. I don't like to do this unless I absolutely have to. It's just a lot of mess. So let's go ahead and complete the square. So remember, the idea behind completing the square is that we don't have the right c value. So we're going to shift the negative 8 to the right-hand side by adding it, making it plus 8, and we're going to search for a better c value. A lot of people have kind of latched onto this box method, which I think is fantastic. Use it as long as it works for you. So we're going to build this quadratic in this box. So x squared definitely goes here, making sure the sides are going to be x and x. 4x will occupy the 2 corners, in half, of course, so that's going to be plus 2x, because plus 2 make 4, which means the dimensions of our box are plus 2, which means our missing c value is a plus 4, because 2 times 2 is, of course, 4. So we add 4 to the left, add 4 to the right to compensate, because we've got to keep the equation balanced. And so now this quadratic can be rewritten as x plus 2 quantity squared, because x plus 2 times x plus 2 is a number times itself, and that's going to equal 12. So now we're going to square root both sides. So x plus 2 is equal to plus and minus square root of 12. And then subtract 2 on both sides, so x is equal to plus or minus square root of 12 plus 2. Now that's a pretty messy way to write it. We can make a couple notes here, namely that if we take the square root of 12, we can break that down to square root of 4 times square root of 3, which means we can rewrite square root of 12 as 2 square roots of 3. And typically we're going to write the single number in front, so we can actually write this as x equals 2 plus or minus 2 square roots of 3. Okay, and those are going to be our 2 zeros for this particular function. All right, so let's move on to some ACT prep. So if m is a list of distinct prime factors of 100, then what is the value of 3m? Okay. So we have to kind of analyze what this term prime factors means. So when you talk about 100, we can factor it, which means find the numbers that multiply it back to 100. But those aren't all necessarily prime factors. Prime, if you recall, is a number that has only 2 factors, 1 itself. So a number like 2 is a prime number, a number like 7 is a prime number, because those kind of numbers like 2 can only be multiplied by 1 in itself. And 7 can only break down into 1 itself, as opposed to a number like 25 that has multiple factors. You can break it down into like 5 and 5 in addition to 1 and 25. Okay? But this kind of thinking, this kind of factoring tree is how to actually attack this problem, I think, efficiently. And so if I want to find the list of distinct and prime factors of 100, we can just actually start doing a factoring tree. So what I mean is this. So let's break this first down into 2 and 50. Okay? 50 can further be broken down into 2 and 25. And then 25 can be broken down into 5 and 5. And so once you reach the end of this tree, once you can't factor any further, please notice that all you have left are going to be 2's and 5's. And so if I'm looking at the distinct prime factors of 100, I can actually just say it's 2, 2, 5, and 5. Okay? You can check that by multiplying this all back together. If you take 2 times 2 times 5 times 5, that's 100. So that's a list of the full prime factors of 100. Now this asks for the distinct prime factors of 100, and so it's important to note that's just 2 and 5. And so then now the question is actually asking, then what is the value of 3 times m? So we can see this list has 2 elements. So we have a 2 and a 5. And so if they're asking for 3m, if there's 2 elements in the set, so 3m would be the same as 3 times 2, which makes the answer 6. Alright, which of the following values of x satisfies the inequality 3 over 2 is less than x is less than 5 over 2? So there's a couple different ways we can approach this, but first we have to make sure we understand like what's going on with the value here. So we have this x that's trapped in between 2 values, in between square root 3 over 2 and 5 over 2, and then we're given like a bunch of these values to try to check against it. Now, one way we can attack this is to like look at these values and try to make some sense of it. So we look at square root of 9 over 2. That's the same thing as like 3 over 2. If we look at square root of 20 over 2, that's not, we can't like pull out an exact value, but what we can do is look at square root of 20 and say, well, it's in between a couple numbers. And so if you think about the square root of 20, it's got to be between, say, 4 and 5. So square root of 20 is trapped between 4 and 5, because 4 times 4 is 16, 5 times 5 is 25, so it's right in between there. We can do the same thing with this, except that's actually just going to be 5 over 2. 29, so 29 will be in between 5 and 6, because again, 5 times 5 is 25, which is less than 29. 6 times 6 is 36, which is above it. And 31 has to be between 6 and 7. And so if we look at our choices, we can eliminate a couple right away. Notice that these are strictly less than and strictly greater than signs. So immediately we can throw out A and C as an answer. If this has to be in between 5 and 6, this can't be answer either, because we're actually in between 3 and 5. Same thing for 6 and 7, because we have to be trapped between 3 and 5. So the only answer that's viable is going to be B, because square root of 20 is trapped between 4 and 5, and of course it's over 2. Right? So B has to be our only answer. So even though you don't know the actual, don't know the actual squared values, you could calculate them, but it's just as fast to kind of estimate their integer values and then compare them against your work. Okay, that does it for homework number 1. This should be a key for homework number 2 coming soon.